Welcome everyone for this distinguished webinar series in AI and cybersecurity at the University of North Dakota. This webinar is co-sponsored by the School of Electrical Engineering and Computer Science and the Centers for AI and Cybersecurity. We are also grateful for other universities supporting this webinar to be, shared with the graduate students in other universities as well. So with me, I'm so grateful for our speaker this week, Dr. Shrirang Abhyankar. And his title is going to be Open Source High Performance Tools at PNNL for Grid Modeling, Simulation, and Learning. And let me give a quick background of Dr. Shrirang. Dr. Shrirang Abhyankar is a senior scientist with Electricity Infrastructure and Buildings Division at Pacific Northwest National Lab. Prior to PNNL, he was with Argonne National Lab, working with mathematics and computer science and energy system divisions. He received MS and Ph.D. in electrical engineering from Illinois Institute of Technology, Chicago. Dr. Abhyankar has contributed to various open source projects, including GridPACK, HELICS, PETSc/TAO, and MATPOWER. With this, the floor is yours, Dr. Shrirang. Thank you so much again. I'm so grateful for you taking your time and effort to share this presentation with us.
Thank you, Prakash. Thank you for that introduction, and thank you for this invitation to present some of the work that me and my colleagues have done at PNNL. So let me share my screen over here, and then we can get started. Can you see my screen? Is the slide full screen?
That's perfect, Dr. Abhyankar. Yep.
Okay, great. Thank you. All right. So thank you, everyone, for joining this webinar. I am, it's a
Sorry to interrupt you, Dr. Abhyankar. I think you might have to make it full screen.
Okay, that's what I thought. Hang on.
Sorry.
How about now?
Yeah, it's perfect now. Yeah.
Okay. All right. It's a pleasure to give this talk and presenting some of the open source high performance tools that we are developing at PNNL, specifically around grid modeling, simulation, and also on learning. These are some of the open source tools that I'll be talking about. I think I'll be presenting about 4 or 5 different tools that we've developed at the lab. And I'll give a little bit more details on a couple of tools. These tools have been in development over a number of years now. Some of the tools have been in development for about 10-ish years or so, and some of them are more recent, about 3 or 4 years. Given the time constraints, I won't go into the detail of the math and how the tool is used and any of those intricate details. What I'll present here is an overview of these tools, and if you have any questions on these tools, feel free to send me an email. Feel free to reach out, and I can give more details about that. Let me also just 1 second here. Okay. What I want to do is I want to stop the video so that there is more bandwidth. Sometimes when I have the video on, the bandwidth is less. Okay. Can you all see the screen again?
Yeah, we can see it, Dr. Abhyankar.
Okay, thank you. Sorry for that, slight deviation. Okay, so first of all, I just wanted to give a brief background on national labs and PNNL. So in total, there are 17 national laboratories here in the US, which are under the Department of Energy, both on the East Coast and the West Coast. And, the national labs do critical research on, lots of challenges that the country is facing, from electricity grid to materials to computational science. And, there are lots of resources at different national laboratory centers and so on. PNNL is located in Washington State. So the northwest corner, the logo that you see, PNNL, that's where we are located. It's in a city called Richland. It's called Tri-City, so there are 3 cities, and Richland is where the main lab is located. We also have offices in Seattle and Portland as well. This is kind of a general overlay of how how PNNL looks like. There are different buildings, and a lot of different research from material science to nuclear to energy systems, chemistry, computer science, and so on. There are two big buildings or centers that are coming up. There is an energy sciences center, which is more on the chemistry, atmosphere, machine learning, and it's still under development. And we are also excited to have this grid storage launchpad. So basically, there is a new facility coming up dedicated for research around storage and all facets of storage, including short-term, long-term storage, as well as it will be a center or a facility where external people can come and do the testing, as well as do research collaborations and so on. So that grid storage facility will be, I think it should be maybe in a couple of years or a little more than that, and it just got started. So slightly, going back to the main topic of the presentation. So I want to start off with, how the grid is evolving. And, particularly, I also want to, say this to the graduate students and the students, undergrads who are listening over here, that this is a really exciting time to be in this field, because, electrification is at the core in the future. So you might have heard about electrification of vehicles, decarbonization, electrification of your heating systems, and so on and so forth. So a big push towards decarbonization is electrifying these different facilities, including buildings and so on. So there is a lot of research, a lot of push towards electrification, and the electric grid is going to be at the center of it. And so there is a lot of exciting stuff to come in the near future. And so this is, if you're studying electric power grid right now, it's amazing to be in this field right now. And the grid, how it was in previously just with electromechanical generators, right from Edison's times to Tesla. Mostly the focus was on synchronous generator, fossil fuel generators. But now there's a big push towards renewable energy. And, if you listen to, there was a webinar by DOE yesterday on Atlantic grid offshore technology. So basically, the push is towards deploying 30 gigawatt of offshore wind to the grid by 2030, and then floating offshore wind by 2035. So there is a big push for renewable penetration, basically to reduce the carbon footprint. With the renewable penetration, there also comes these newer technologies of how those renewable energy sources are integrated with the grid. So there are these inverter-based interfaces. Basically, these are power electronics driven interfaces. There are different types of inverter technologies. There are grid forming and grid following. Grid following inverters are the traditional inverter sources. Grid forming ones are what is touted as the next generation inverter technology that is needed to support that much amount of renewable energy integration. On the demand side, there is you would have seen solar panels on rooftops. There is distributed generation, which means you can have batteries at home. So suddenly now the consumers of electricity are not just the consumers, but they can produce electricity as well, and they can provide energy back to the grid. And this is this was not before, because the grid was designed and planned as a one-way flow of electricity from your generators to the houses or to the loads. But now you have loads that can produce electricity as well. So there is an interesting challenge now how to manage the grid. There is a lot of sensors coming in for more visibility on the grid. PMUs or phasor measurement units are based on or deployed on the transmission grid to monitor the grid frequency voltages at at a rate of 30 to 60 times per second. AMIs, which are more on the local level or at the house level. You might have seen meters or electronic meters that can directly provide a signal back to your utility and so on. But along with this, you might have also heard about climate change, and the effect of that has been there has been an increasing number of disruptions on the grid, be it due to climate change. So you've seen effects of hurricanes, wildfires, tornadoes. Recently, there was a flood in California that caused disruptions as well. There are man-made disruptions, some either due to cyber security reasons or due to man-made attacks. So these are also increasing, and so there's really a need to understand how the grid behaves and how it will turn out in the future. Talking about decarbonization, some of the trends that we are seeing in decarbonization, the expectation is that the capacity from renewable energy sources from now up to 2050 will increase by 3.5 times. So suddenly, it's a lot of wind energy, and there is expectation that the coal or the conventional generation sources or the fossil fuel generation sources are going to retire. Now, this leads to a number of challenges because the conventional generation sources were thought of dispatchable generation sources. What that means is if an operator says that gives a signal to the coal power plant to increase its output by, let's say, 50 megawatt, the coal power plant would be able to do that because it can burn extra coal or extra fuel and can provide that much amount of energy. But if you give the same signal to a wind farm or a wind power plant, the challenge is you don't know whether there is sufficient wind blowing or not. So that kind of leads to this uncertainty whether your new renewable generation sources will provide that much amount of electricity on demand or not. The conventional generation sources also were these bulky big machines, which used to provide what is called as inertia. Basically, in a nutshell, that means that if there is any disturbance on the grid, then that the impact of that disturbance would not be very, very fast or would not propagate fast enough. But these newer machines or these new renewable energy sources, they come with the inverter-based technologies, and that has a trend of reducing the inertia, or in a nutshell, the impact is much more faster. The dip in voltage and frequencies could be much more faster. So how do you so tuning these power electronic interfaces or sources is an ongoing research right now. So I come from, my emphasis and my group's emphasis here at PNNL is on modeling and simulation. So how do you model the power grid? What sort of models do you need for what time scales and so on? And because of these, system challenges, the trends that we are seeing in modeling and simulation is there is a large number of scenarios that you need to study. And this is because, you don't have a good understanding or forecast of how the wind is going to blow or how the solar energy or how the sun is going to shine. So that adds to this uncertainty, or, now instead of just looking at one wind penetration level, now you need to understand or study different penetration level, which means that you need to study lots of what if scenarios. I talked about power electronics. Power electronics is going to be, one of the main assets deployed on the grid. And when you have power electronics, you don't necessarily have perfect sinusoidal waves, and that gives rise to harmonics. And to study harmonics, you need to go to what is called as EMT, or electromagnetic transient model. And the challenge with electromagnetic transient model is that it's very, very high fidelity model. So you can study it use it to study smaller systems. But once you go on to larger, like regional scale or utility scale system, the computational burden is just too much, and which causes the simulation to become extremely slow. A few of the challenges that we are seeing for analysis tools here. First one is, and these are some of my thoughts. There will be lots of other challenges to the analysis tools. So the first one is transmission plus distribution, and what I mean by that is right now in the industry, there are tools for just the transmission system analysis, basically anything that is 69 kilovolt and up system, so the backbone system. So there are tools for the transmission system and there are tools for the distribution system. But because of all the reverse flow of electricity from your your solar panels, your local generation, now there is a need to understand how the power flows between transmission and distribution. So you can't just have tools for transmission or tools for distribution. So there is a push towards combining these tools and study the impact on the entire grid as one, as opposed to just on transmission or just on distribution. I mentioned about uncertainty and variability and increase in the number of scenarios. So that's another challenge here. Need of faster scale dynamics, which is the figure on the right. What you see are these instantaneous sinusoidal signals that you need to see, that you need to analyze. But when you try to analyze it for a large scale system, it becomes very computationally challenging. And obviously computational challenges and longer simulation time. So one of the unique factors about grid planning and operation is that since the electricity flows instantaneously or nearly instantaneously, our planning and analysis tool also are time constrained. What that means is that whatever analysis that you're running, that needs to finish in a certain time frame. So for example, if you are doing an hour ahead planning, then your analysis tool needs to finish its operation, or needs to execute less than an hour. And as you go on increasing the fidelity, the number of scenarios and so on, there is a big challenge of how to how can we do that in a time constrained manner. All right, so I'm going to be focusing now on some of the tools that we are developing here at the lab. So as I mentioned, PNNL has a lot of development and a lot of expertise in developing these tools. And one of the things, or one of the things that we really try to push towards is on developing open source tools. And we really like to develop open source tools because that fosters collaboration, as well as the tool is not just limited to the research at the lab, but it helps the community as well. And I call these tools as high performance tools because not only can they run on your laptop, but if you want to run these calculations on bigger clusters or bigger supercomputers, these tools can run on those platforms as well. And really for bigger problems, if you want to solve, your local laptop or your local cluster may not be enough. So you need to really scale the analysis. And so the tools that we develop here are also scalable in that sense. The figure at the left is what I'm showing here are the different time scales and the different tools that cater to those time scales. So for example, HELICS is one of the tools which is developed at PNNL. Actually, it's co-developed by PNNL along with other national laboratories. It's a tool for co-simulation. And so co-simulation is basically you're orchestrating different tools to do a kind of a unified or a common analysis. And so HELICS can work across these different time scales. There is ExaGO for economic dispatch, which is around minutes to days kind of time scale. Hippo is another tool for a security constraint unit commitment. And then if you want to go to finer time scales, which is on the microsecond or the millisecond level, then there is a tool called GridPACK, which is used for that purpose. These tools are, basically these tools model the physics of the grid. But ultimately, in an analysis tool, that physics is translated into matrices and vectors, or equations, and those equations need to be solved. And so you need these numerical libraries that solve these different equations. And so we collaborate with different labs, and as well as our folks in math and computer science at PNNL. And so we use those numerical libraries to really accelerate our our power grid tools. And I've mentioned a number of different libraries that we use, and these are funded by an office called ASCR, Advanced Scientific Computing Research, which is another DOE Office of Science office. Okay, so I'll talk briefly about some of the tools now, and then I'll go a little deep into some of the tools. So the first tool that I want to introduce here is a tool called GridLab-D. It's primarily used for distribution system analysis. So it does unbalanced three-phase distribution analysis. It's been in development for, I think, over about 10 or 12 years now, and it does detailed modeling of distribution systems along with unbalanced three-phase networks. It has models of houses as well, different kinds of loads. It does power flow, time series analysis, and recently GridLab-D has also started doing dynamics, which is basically trying to understand if there is a fault on the distribution grid, then how are the inverters and how are the devices impacted. It's also got detailed models of end use load. So it has models of your HVAC system, your other resistive and other types of load. It's used in a number of different applications by different entities. I've given some examples over here: automation design, peak load management, storage, rate structure analysis, and so on. And I've given a link at the bottom for that tool. The second tool, which is on the right, is called HELICS. So HELICS is a co-simulation framework to integrate different simulators. So what that means is if you want to do, let's say, a transmission and a distribution system analysis, you have GridLab-D for distribution system analysis. So that's one simulator. And let's say if you have PSSE as another simulator, which is on the transmission side, HELICS helps to integrate those two tools, or basically pass messages between PSSE and GridLab-D so that you can do a co-simulation. And it's not limited to just power grid tools. If you are doing a simulation which requires different tools or different simulators to be orchestrated, to be interfaced, then HELICS is a tool that can do that job for you. It's developed, as I said, by several national labs, and there are a number of examples on the HELICS website of different applications, including transmission distribution. There is a project going on gas electric grid interdependency, and so on. And you can get more information about HELICS on at the link that I've shown at the bottom. The third tool that I want to introduce is called HIPPO. So HIPPO is used for security constraint unit commitment. So security constraint unit commitment, or day-ahead SCUC, is one of the main applications that is used in the electricity markets right now. So every day the ISOs run security constraint unit application to figure out which generator should be dispatched, which generator should be on and off, how much reserve should be there, and so on. So HIPPO models that SCUC application, but it also incorporates high performance computing to accelerate the day-ahead unit commitment. And it uses some advanced algorithm for solving mixed integer problems, because that's the nature of that problem. And it's been tested, and there is a close collaboration with MISO, who were testing HIPPO. There is a link again at the bottom, which will have more information on HIPPO. The fourth tool is called GridPACK, and I'll present more slides on GridPACK and what it is and so on. So GridPACK is essentially, it's a framework. First and foremost, it is a framework for application development. And what that means is, if you're trying to develop a new power grid application, let's say a power flow, and if you want to run it on a parallel computer or a cluster, then GridPACK will provides you kind of the building blocks by which you can develop your application. So GridPACK has a number of different blocks, like matrices and vectors and buses and generators and lines that you can use to develop your application. So you won't have to like reinvent the wheel, but you just use those blocks and put them together to develop your application. It interfaces with state-of-the-art numerical solvers, parallel numerical solvers. So there's a library called PETSc that we interface with. It has a number of different applications: power flow, state estimation, contingency analysis. And I'm going to be specifically focusing on the last application, which is the dynamics, or basically this is, as I mentioned, in the time scale of milliseconds. And really the focus of dynamics or transient stability, if you might have heard, is what happens to the grid if there are major disturbances, like what happens to the how do the dynamics evolve when there is a fault, when there is a generator tripping or a line tripping, and so on. And traditionally, as I mentioned, the conventional generators were only synchronous generators, but now there is this push towards renewable energy generators. So we've started in GridPACK adding models of renewable energy generators, which I'll show in a second, and really trying to understand, when you push towards 20%, 30%, 40%, and so on and so forth of renewable energy generation, what happens to the grid? How does the grid evolve and react to it? Also, I just wanted to mention some of the latest additions to GridPACK. So I mentioned about dynamics and about studying faults and contingencies and so on. So there are a couple of additions that we have or under development for GridPACK. The first one is an application called Dynamic Security Assessment. So here the main aim is that if you are given lots of different forecasts of wind energy or wind generation, and if you want to study what is the impact of faults or disturbances on these different scenarios, that involves studying a lot of what-if scenarios. So first of all, for each scenario, you need to have different contingencies, and then put that analysis together and figure out what is kind of the range, or what is the overall impact. And so, as I mentioned, this involves a lot of studying a lot of different scenarios. And so what GridPACK does is, since these scenarios are kind of individual scenarios, GridPACK can parallelize these scenarios. So each processor will run a different contingency or scenario. And then at the end, it will collect the information from all the different scenarios with respect to the frequencies, voltages, and so on. And it will create these statistics of what the overall envelope or overall statistics look like. So that's the first application. The second application, which is kind of under development, is on this EMT simulation engine. As I mentioned to you before, that running EMT analysis or electromagnetic transient analysis on large scale grids is very computationally burdensome. So we are trying to accelerate this EMT application, develop an EMT application using high performance computing that will be parallel, and then trying out different numerical integration algorithms as well as numerical solution algorithms, and really trying to see how much we can accelerate this EMT simulation. And the goal here is to enable EMT simulation for large scale systems. Over the last year or so, we've added a lot of renewable energy models, and these models are from WEC, and WEC has developed a lot of generic models for representing renewable energy models. And I won't go deep into the details of this, but there are these different wind plant models of different types depending on what is the configuration of the wind plant. So there are type 3, type 4. Currently, the type 4 is the one that is prevalent in the industry. And so in order to represent these wind plant models, on the right is what I'm showing is the the different components of these wind plants. So there are these different WEC generic models that have been proposed by WEC. And so we model all these different components. Along with that, we have models of grid forming inverters, as well as some of the newer models which are being still investigated by WEC, but they are not available yet. And with GridPACK, you can, so you can do a simulation with large penetration of wind generator models. We've compared our models against commercial software tools to make sure that they work. There are a number of test systems that are available. So there is this Kundur 2 area network, as well as a 240 bus system developed by NREL. So you can try that out. And the plots on the right, I'll just briefly mention about the bottom two plots. What is shown over here is how do the dynamics look like after, for a particular fault scenario. So the left bottom figure is the dynamics of the renewable generators. And on the right is the dynamics of the synchronous machines or the non-renewable generators. And you can see a stark difference between these two. So for the synchronous generator machine, there is this oscillatory behavior because of this large electromechanical inertia. So there is this oscillatory behavior before the electrical power, the dynamics settle down. But for the renewable energy generators, there is this sharp spike at the instant of the disturbance, but then the recovery is very fast. And that is what the characteristic of the renewable energy generators is as well, that they have a faster recovery because of the power electronics involved and everything. So in the future, how this, once you have a lot of this power electronics equipment or the renewable energy model, how will it behave on the grid? That's kind of one of the research directions that a lot of people are pursuing right now. The next tool that I want to introduce, and something that we've been working for the last 3 or 4 years now, is a tool called Exascale Grid Optimization, or ExaGO. And this is a toolkit for optimization, and the time scales of interest here are from minutes to hours or days. And we don't model the dynamics, what I showed in GridPACK, but this is more on kind of steady state power flow sort of modeling framework. So again, it's an open source tool. And for the optimization, you can incorporate uncertainties, that is renewable integration, which is basically your different wind forecast and so on. You can model different outages. So generator outages, line outages, and others, you can model that, as well as you can study the optimization over a period of time. So let's say if you want to see how is the dispatch going to be for the next 4 hours or 5 hours, then ExaGO will do the optimization and will try to find the optimal dispatch for those 4 or 5 hours. It's based on high performance computing. A differentiating factor for ExaGO is that we are also using graphical processing units or GPUs, and trying to understand how do GPUs perform for such kind of applications. So GPUs, if you're aware, they are heavily used right now for a number of different applications, from computer vision to machine learning to gaming industry. And those applications are, really work well with GPUs because of the nature of those applications. But when it comes to scientific computing or optimization or numerical solver operations, GPUs are not necessarily the ideal platform. So we are trying to understand, how can we develop applications or develop solvers on the GPUs as a part of this as well. There are scalable algorithms, so you can run it for large number of scenarios with large number of contingencies and so on. One thing that we are developing for ExaGO is visualization. So you can visualize your output through like a graphical, through a web-based interface, and at the bottom are some of the visualization that we've developed to visualize the electricity flows, to visualize the heat maps, or basically where is the load concentrated and so on, as well as the generation. So you can visualize the output. It has a Python API as well. And so if you're interested, you can use the Python API for this application. Nirup, just a quick check on time. How am I doing on time?
Yeah, Dr. Abhyankar, you have about 10 more minutes for your talk.
Okay, perfect. Thank
You're
you.
good. Yeah.
Okay, so I'll just speed it up a little bit because I have a few more slides. So as I mentioned, ExaGO, is a toolkit for large-scale optimization. You can, it takes in inputs from Wind toolkit to generate the wind scenarios. Cyber is one of the things that we really want to integrate in the future. Right now, we don't have that, but if there is interest, then we can talk about that. We incorporate outages as well. So, your N-1 or N-A outages. And what ExaGO does is it runs this large scale ACOPF optimization and produces, what should be the best possible dispatch given, the contingencies, wind scenarios, and so on. So ExaGO has a number of different applications, and I'm going to quickly walk through what the different applications or what you can use in ExaGO. So the first and the foremost application is the AC optimal power flow, which is one of the core applications in Power Grid. Basically, it does a nonlinear AC optimal power flow. In OP flow, which is the AC optimal power flow application, we have a number of features, typical features like line flow limits, voltages, and so on. There are some advanced features like PV/PQ switching, automatic governor control, ramp limits, and so on. You can also figure out what is if a AC optimal power flow is not feasible, which means that there is no solution for it, then it will also provide how much amount of load shed you need to do to get a feasible solution. So there is addition of load curtailment as well as bus power imbalance. We use state-of-the-art libraries, optimization libraries. So IPOP is one of the, a big open source library for optimization. Another library that we are using in this project is called HIOP, which is developed by Lawrence Livermore National Lab. The second application of ExaGO is to study multi-period events. So what should be the dispatch for a given horizon? And it gives rise to the structure that you're seeing on the left bottom. So you have these different time steps that are coupled, and basically they're coupled by the ramping constraints, or how much ramping can a generator do from one time step to another time step. And the time step is given by the user in terms of whether it be 5 minutes, half an hour, 1 hour, or so on. And ExaGO will then decide based on the time step how much ramping is allowed for the generators. The formulation I've given on the right, which is basically this multi-period formulation. Again, this is nonlinear ACOPF, but now you have these time constraints and so on. And the figure at the bottom is just one example output from this application, which shows how the different generators or how the different generator types evolve over time for a given simulation. The third application is a security constraint optimal power flow, or SCOPF. This is also one of the core applications run in the industry to figure out, for a given dispatch, whether if any of the contingencies do occur, which is basically N-1, then the system will be secure. And so the question that this SCOPF is trying to address is, what should be my here and now dispatch such that if any of these contingencies do occur, then the system will be secure for that contingency condition. And if it is not, then what should be the amount of the optimal load loss or optimal control actions that I can take? I won't go deep into the details of the application, but the structure of the application is shown at the bottom over here. So C0 is your base condition or the base case, and you have these different contingencies, C1, C2, and C3. And so you need to figure out what should be the dispatch in C0 such that C1, C2, C3 are secure. The formulation is on the top right. What we use, so this can be a large problem because let's say if you're running the WEC 10,000 bus system, then it can have about 20,000 or 30,000 contingencies. And so this becomes like a gigantic problem. So you need to really parallelize this problem, and you cannot run this on just a single machine. So we have this library called HIOP, and it has a primal decomposition based parallel algorithm in order to solve this. So we use that algorithm for solving it. So essentially what it does is each contingency is assigned to a separate processor, and then it goes iterating between the what is called as the base processor and the rank 0, and then all the other contingencies and so on. The last application for this ExaGO that I want to talk about is this stochastic security constraint optimal power flow. So in the last slide, I just mentioned the security constraint, which means what is the impact for contingencies. But then you also have, if you have stochasticity, basically you have uncertainties due to wind. You need to incorporate those as well. So this application tries to figure out what should be the best dispatch for any of the wind generation forecasts, as well as any of those contingencies that happen within them. So it's kind of a two-level or a two-stage where S0 and S1 here shown in the figure are the wind scenarios, and then for each wind scenario you'll have contingencies. The formulation I've given on the right, and last year we ran this on the 10,000, the Texas 2000 bus system with about 10 different wind scenario and 1,000 contingencies. So in total about 10,000 scenarios, and we were able to scale it down to under 15 minutes, going from more than I don't know how many hours and so on. So so this is an example of like really running a large scale optimization application and running it at scale so that your total computation time is reduced. I'm going to be moving on in the last 5 minutes or so. I'm going to be moving on the learning side of things, or the machine learning, and I'm going to be introducing or quickly talking about a library called Neuromancer. But before that, I just want to to cover this. There are these different solution methods that you have for different applications. So there are some applications which are optimization based, so you need to optimize something, and these are all model based, or requires prior knowledge of physics, developed from the first principles, the models, and so on. The other category of applications stem from differential equations. So this could be either partial differential equations or your ODEs or whatnot. Again, there are models for this, and it requires more domain knowledge to it. On the learning side of things, there are applications stemming from supervised learning. So which is basically you're given a set of targets and you want to train your model such that it tries to minimize the distance between the target and your model. So that's the labeled output. There is reinforcement models based on reinforcement learning as well, which basically you need to interact with the environment, and then there is a reward function which says how close are you to the actual behavior or to the model behavior. And so both the supervised learning and reinforcement learning, they don't require information of the model itself, but they actually learn the model from the data. And in recent years, there has been, like a big emphasis on data-driven modeling. And so there are these different models. So there is a white box model, which is basically your physics model. So the physics. There is a gray box model, which has this combination of your physics. So some part of your physics, but you don't know some other part of the physics. So you model that with a neural network or what have you. And on the other spectrum is a full black box model, where you don't know anything about your model. So you put that as a neural network. And in order to train the model, you have to go through these different architectures of how you set up your neural network, different layers, how many neurons, and what sort of activation functions, and all that stuff. And so so really you're going as you go from white box to black box, there is this push or move from more domain knowledge to less domain knowledge. And over the last, I want to say, a decade or so, or maybe even less than 5 years, I think there has been a lot of work done on trying to model the physics in a number of different ways. There is the physics-based model, which I talked about, the white box, but then, this gray box model where you can assign what are called as physics priors, or some knowledge of what the model has. There are neural ODEs, or neural ordinary different equations, which is an exciting field, which is basically trying to learn the model, the differential equations. There are these graph neural networks, which is basically a learning based on a graph-based topology. You can even have a state space model. So instead of you pose your model as a state space model, and basically, x dot equals ax plus bu and y equals cx plus du. And then each of these A, B, C, D blocks for the state space are neural networks, and you're trying to learn that. And in terms of the tools, you have a number of different solution tools. So for online optimization, there are a number of different tools for differential equations. For supervised learning and reinforcement learning, there is PyTorch, TensorFlow, GIM, and so on. So there are tools that are specific for model-based solutions, and then there are tools that are specific for the learning-based solutions. And so there is this library which is being developed at the lab, which really tries to see how can you interface or integrate these different model-based techniques with the learning-based techniques. And it's in this context of differential programming, or basically trying to unify this data-driven modeling and optimization based on automatic differentiation, because automatic differentiation libraries are kind of inbuilt into this PyTorch and other libraries as well. So there's this library called Neuromancer, which I've talked about. So it's an open source scientific machine library again. It has a number of different features. So you can do parametric nonlinear programs. So basically, it's an optimization problem with a number of different parameters. You can do constrained machine learning. There is physics-informed machine learning for dynamical systems. There are neural state space model as well as neural ordinary differential equations. And then you can use it for your control applications as well. I won't go deep into this library because this is not what I work on, but if you need more information, you can go to the GitHub page for Neuromancer, where there is a lot of information about the library, and including there are training videos on getting started with the library as well. I'll skip this application in the interest of time, but just briefly, this is an application where we were trying to incorporate the dynamics in optimization, and the dynamics is not really included in the optimization. And so what we're trying to do here is to learn the dynamics through Neuromancer, or using a neural state space model, and then plug that into optimization. And if you're interested, there's a paper that I've shown at the bottom, and you can take a look at that. So this is one of the preliminary works that we did on introducing dynamics in optimization through a learning-based machine. I'd like to conclude with just a few links of the different tools that I talked about here. These are all open source tools. These are active tools that are under development and have been in development for a number of years now, and will be expected to be in development in the future as well. So if anyone is interested, I'd encourage you to go to these sites, take a look, let us know what you think of it, and we'll be happy to get you started on these tools. So with that, I want to thank everyone for listening, and I will be happy to answer any questions that you have.
Thank you, Shri, for your exciting presentation. So Nirup, do you see any Q&A from chat?
Yes, so there is one question. Dr. Shrirang, could you provide some information about the team size and time span of the development of the major open source course simulation packages?
Sorry, could you repeat that question?
Yeah. Could you provide some information about the team size and time span of the development of the major open source course simulation packages?
I mean, maybe in some sense, like how long this development of these tools have done? Is it already ready to go or still in the development? Could you give me your experience in how this effort has streamlined by PNNL?
Yeah, sure. So, okay, so the time scale of, or the so the time scale of the library is varied across these different tools. So for example, GridLab-D is one of our oldest tools, which has been there for 10 to 12 years. And the team size varies from project to project, who is there, but usually there is at least about 5 to 6 people who are involved in the development of packages. Not only there is development, but then there is doing the testing of the tool, putting it on GitHub, answering issues, working with specific folks who want to use the library. So GridLab-D, yes, it has been for about 10 or 12 years now, and it, as I said, it's looking on the distribution system side of things. HELICS, it was first I think introduced in 2017 or 18, and HELICS is developed or co-developed by different national labs, mainly PNNL, NREL, and PNNL, NREL, and Lawrence Livermore. These are the three main labs, and so it has been there for almost since 2016 or 2017 now, so about 6 or 7 years. GridPACK about 10ish years or so. So I'm one of the co-leads for GridPACK right now, and we have on our team about 6 or 7 people who work on various different aspects. And in the past, there were other folks who had been there or not there as well. ExaGO is again 4 years old. Neuromancer is again 3 or 4 years old, and each of them have minimum, I want to say, 3 to 4 people who are working on the development of this library. And we work across different projects, so we get experience from different projects, different applications, and then in order to this is, I think, open source tools is one of the way where you can gather knowledge from working across these different projects and put it together, so that it shouldn't be like once the project finishes, you don't you have to start from scratch for some other project. I think open source tools allows us to kind of reuse the knowledge that we've gained from past projects and then utilize it for the future projects.
I have another question. And how is this interoperability between all these GridPACK and ExaGO tools? I'm not sure. And are they all integrated well in terms of working? Importing files from one tool versus the other tool, or how many clients do you have using these tools? Are they using any? Do we have access to the training models? People have already utilized these tools. Is also made available. Do you have any so that people can able to start see how they can also learn from what others have, how the way the tool is used?
Yeah, that's an excellent question, Prakash. So GridPACK, and apart from HELICS, all the other tools are kind of domain specific and cater to a certain application. So for example, GridPACK caters to the dynamics. ExaGO caters to the optimization application. GridLab-D caters to the distribution system analysis. And there is no unifying or no, what I want to say is no tool that kind of covers the entire spectrum of these different applications, and it becomes hard to manage everything. So right now there are these different tools, and the kind of the way that we see is HELICS as one of the central kind of co-simulation tool that orchestrates these different tools. There are examples on the HELICS repository which show how HELICS can be used to connect different simulators, and so that can be used as a starting example. There are libraries such as GridLab-D, which actually have HELICS interfaced in them, so you can use HELICS with them directly. With respect to learning, Neuromancer has Neuromancer is a library dedicated for learning, and I want to also say that though I've presented all the tools in the power grid context over here. Neuromancer is not specifically dedicated to power grid, but it is more general AI and machine learning library. And Neuromancer has a number of different examples, and by which you can see the the code. You can see the Python code and use that as an example or as a template for starting your own application.
Great, thank you. Nirup, do you see any other questions?
Question. What are some of the challenges associated with developing and maintaining open source software tools? And also, how have these challenges been addressed in the context of the PNNL toolset?
Yeah, that's an excellent question as well. So in terms of development, like open source tools, again, we don't have like dedicated funding for open source tools. We have the tools funded through activities across these different projects. So the different projects use these libraries, and through these projects is where we we do the development of the library. So the challenges, what I've seen is you want to write an open source library which is usable and which is performant, and it is it has a nice structure and everything, and that's always a challenge, because you have time constraints of the project deliverables versus wishes and wish list that you have for the library. So that's one challenge I want to say. The second challenge is maintaining the code is definitely one of the challenges, because there are different people who write code in different way, and so what we have right now, in order to kind of have some sort of a regulation over the code, is we basically anyone who writes the code has to go through what is called as a pull request process. So they submit a pull request, someone reviews the code, and then once all the tests pass, once all the the questions are answered, that's when we integrate that feature in the library. And this is kind of a general learning from the more general open source community as well. Sorry, what was the second question? I forgot.
The second question is related to the first one. It says, how have these challenges been addressed in the context of the PNNL toolset? I think you had mentioned a little bit of that.
I think you addressed that question already.
Okay.
Anyway, in the interest of time, I think we're going to thank the speaker for his time, and appreciate so much for putting your effort towards this presentation. And we will be sending you a plaque from UND as a token of appreciation. And thank you, Dr. Shrirang, for your time, and thank you, Nirup, for coordinating this.
Yeah, thank you, Prakash and Nirup, for this opportunity, and thank you all for listening.
Thank you, Dr. Abhyankar.
Thank you.